Welcome everyone for the fourth week lecture for an introduction to climate dynamics and variability and monitoring course of NPTEL. Today, as per our previous classes, we will discuss some current week MCQ and also some previous week MCQ. So, this is our first question for today. You can unmute yourself or you can write the answer in the chat box. And when there is any discussion needed, we will see the discussion after giving the answer to the MCQ. So, question 1 for today: which of the following statements are true for a unstable atmosphere? Option 1 is vertical transport of water vapor and energy is difficult. Buoyancy driven convection currents are weak. C is large scale cloud formation and the precipitation events occurred. And option D is parcel of air will sink back down when lifting force is removed. So there is multiple options correct for this question. So you have to choose those. Which of the following statements are true for a stable atmosphere? So the definition of the stable atmosphere is atmosphere is called stable if a lifted air parcel becomes colder as it moves with the altitude and becomes denser than the surrounding air, so it tends to return and also tends to return to its original position when the lifting force is removed. Mathematically, for the stable atmosphere, the dry air lapse rate is greater than the environmental lapse rate. And this lapse rate, the rate of temperature decrease with the height. So for this question, option A, B and D, both three are correct. Option C is not true. Now, the first option, that is the vertical transport of water vapor is difficult. Vertical transport of water vapor and energy is difficult. As in the stable condition, vertical motion of air is suppressed. So, vertical transport or the vertical mixing of different kind of gases or the vertical movement of energy is limited in the stable atmospheric condition. Option B, buoyancy driven convection currents are weak. This is also true because in the stable environment, buoyant force oppose motion, that implies there is weak or no convection, and convection relies on the instability mainly. So as there is no instability, so there is no convection, you can say. And option C, as there is no instability, there is no formation of large scale cloud formation. So option C, where they are saying that large scale cloud formation on precipitation event will happen, that option is incorrect for a stable atmosphere. And option D is the classic definition of stability, where a parcel of air will sink down back when lifting force is removed. That is, if you displace a parcel upward and then stop pushing, as it is colder and denser than the surrounding, it will sink back. Buoyant force cannot move it upward. So for question A, which of the following statements are true for stable atmosphere? There is a typo here, or there can be MCQ or MOQ type question, this can be within. So for this question, A, B and D, both all the three options are correct, only C is incorrect. Question 2, which of the following conditions indicate a vertically unstable atmosphere for an unsaturated air parcel. Which of the following conditions indicate a vertically unstable atmosphere for an unsaturated air parcel? Here four conditions has been given. One condition is with the lapse rate condition, and another condition is with the potential temperature condition. So which conditions indicate the vertically unstable atmosphere? Here two conditions you have to choose. Which of the following conditions indicate a vertically unstable atmosphere for an unsaturated air parcel? The dry air lapse rate is greater than the environmental lapse rate, or environmental lapse rate is greater than the dry air lapse rate, or the potential temperatures variation with height or altitude is greater than 0, or the potential temperatures variation with height is less than 0. Which of the following two criteria defines the vertically unstable atmosphere? Yes, this option would be B and D are correct. So now we know what is the potential temperature. It is a measure of atmospheric stability where the gradient that is given by the gradient which is termed as the potential temperature. Suppose we have an air parcel that is in some state. The state of an air parcel is defined by two of the following states. One is the temperature, another is the pressure, and how far away above the ground level this air parcel sits. Now the potential temperature is defined such a way that the temperature of this air parcel would attain if it were adiabatically brought from its pressure P to the reference pressure P0. This reference P0 pressure is taken as the 1 bar. Then the potential temperature is defined as potential temperature is equals to T, that is the related to the state of the air parcel, and into P0 by P to the power R by Cp, and P0 is the reference pressure, that is 1 bar or 1000 hectopascal. Now at the altitude Z, if the air parcel is situated at the altitude Z, we can define the potential temperature at that altitude itself. That is here only the temperature T will be a function of at that Z position, and P will be the pressure at that of that air parcel at that altitude. Now also there is another thing, that is the adiabatic lapse rate of the moist air. As the moist air, that the air which contain both dry air and the water vapor, that it rises and cools, its capacity to carry water vapor given by the saturation vapor pressure is fault. Eventually the temperature falls enough that the actual vapor pressure equals to the saturation vapor pressure. Now the rising air has become saturated. If the rising air cools further, water must be condensed out of this air parcel, as its vapor pressure has fallen to the value of the saturation vapor pressure to the new lower vapor pressure corresponding to newer lower temperature, and condensation of water releases a heat, that is the L nu, or known as the latent heat, into air. Thus, the condensation of water in the unsaturated parcel of rising air acts as an internal heat source by releasing the latent heat, which is absorbed by the air parcel. This means that the saturated parcel of air would cool at a slower rate than the equivalent adiabatically moving unsaturated parcel of air. So, you have seen in your lecture notes that the adiabatic lapse rate of the lapse rate of the saturated air or the adiabatic lapse rate of saturated air is less than the lapse rate of the dry air. Now also this saturated lapse rate of the saturated air and the lapse rate of the dry air has a relation which must have the latent heat factor, and also there are other factors Cp, Qs, that is the Qs is the saturation point specific humidity, L nu is the latent heat of the condensation of air, and also there is another definition that is the equivalent potential temperatures definition. So this equivalent potential temperature is the temperature that a moist air parcel at a given state would have if all of its moisture gets condensed out at adiabatic condition, and then it was adiabatically brought to the reference pressure, that is P0, that is taken as 1 bar or 1000 hectopascal. Since the condensation releases heat to the air parcel, so it is found that the theta E, or the equivalent potential temperature, is always greater than the theta, that is the potential temperature, and relation between the two is written as theta E is equals to theta into exponential L nu by Cp Qs by T, where Qs is the saturation point specific humidity and L nu is, that is the latent heat. So we have the three relationship, that are the vertically stable atmosphere, vertically unstable atmosphere, and the conditionally vertically unstable atmosphere. So for the vertically stable atmosphere, it is found that the environmental lapse rate is the lowest, then comes the saturated air's lapse rate, or then comes the dry air lapse rate, and it is found that the potential temperature's gradient is greater than 0, and also the effective potential temperature's gradient is greater than 0, and in the condition 2, which is vertically unstable atmosphere, here vertically unstable atmosphere, of course the saturated air's lapse rate is less than dry air lapse rate, but it is seen that also dry air lapse rate is also less than environmental lapse rate, and also d theta dz is less than 0, and also d theta E by dz is less than 0. And also there is the as another condition, that is the conditionally vertically unstable atmosphere. Here the thing happens, the dry air lapse rate is highest, then comes the environmental lapse rate, then comes the saturated air lapse rate, and also the parameters, that d theta dz is less than 0, but d theta E by dz is greater than 0. So our question 2 was based on the condition 2, that is the vertically unstable atmosphere. So for the vertically unstable atmosphere, we found the environmental lapse rate is greater, then comes the dry air lapse rate, then comes the saturated air lapse rate, and also the potential temperature's gradient is less than 0. Here the rising parcel of air will be hotter than the ambient, and hence for the vertically unstable atmosphere that air parcel would continue to rise. This will be true for both saturated and unsaturated air. Such condition will lead to the strong convective current, vigorous vertical transport of energy, and formation of moisture, cloud, and the precipitation events. Therefore, for the question 2, option B, that is the dry air lapse rate is less than the tau environmental lapse rate, and the B is correct, and also D is correct. A and C are not. A and C are for the condition of the stable atmosphere, vertically stable atmosphere. Now here is the question 3. So question 3 is the math question. A beam of light passes through a cloud with an optical depth of 1.25. The fraction of its original intensity transmitted is dash. And for this kind of question, assume that the radiation is incident perpendicularly to the surface of cloud, and select the closest answer from the following options. Take the cloud as a medium, and then suppose I of the intensity is falling in it. So after the falling, the intensity that is getting transmitted is I0 is falling in it, and it is emitting I, so, or transmitting I. So the formula you know, that is the I is equals to I0 into exponential minus tau. Tau is the factor, that is the optical depth of the medium, that is taken to be 1.25 here. So for this question, so that would be you have to find the fraction of its original intensity transmitted is. So the formula is I is equals to I that is equals to the transmitted intensity, that is equals to the falling intensity into exponential of minus 1.25. Now you have to find the I by I0, that is the fraction of original transmitted intensity. So now that is equal to the exponential of minus 1.25, that is coming around 0.28 something, 286 around that. So for the question 3, option A, 0.29 is the correct answer. Now for the question 4, for a diffuse emitter or diffuse incident radiation, the spectral intensity I lambda is strongly dependent on the direction, on the theta phi direction. This statement is true or false. For a diffuse emitter or diffuse incident radiation case, the spectral intensity I lambda is strongly dependent on the direction theta phi. The statement is true or false. Question 4. This statement is false. For the diffuse emitter or the black body radiator or black body surface or the diffuse incident radiation means the radiation is uniformly distributed across all direction. So if you now assume the r theta phi coordinate, then the spectral intensity is independent of direction for the diffuse emitter. You can just check that the flux density and the intensity, the flux density from the source and the intensity from the source, that is I lambda, both two are related. So this flux can be written as the intensity into the solid angle. And for the diffuse source, it is also found that the flux is also equal to pi into I lambda. Flux is also independent of direction. Therefore, for the diffuse source, both I lambda phi, I theta phi, I lambda as a function of theta phi is equals to I lambda, and I has no directional dependence. Now for question 5, when it comes to the transfer of terrestrial radiation, there is a decrease of spectral intensity in upward direction. This statement is true or false? When it comes to the transfer of terrestrial radiation, there is a decrease in the spectral intensity in upward direction. Is this true or false? This statement, you know that there in the atmosphere there are greenhouse gases. So this gases absorb the radiation which is coming from the earth. So this terrestrial radiation, this term refers to the long wave outgoing long wave radiation or outgoing long wave infrared radiation that is emitted from the earth's surface and atmosphere. As this radiation travel upward through the different layers of atmosphere, it gets absorbed by the greenhouse gases and also it gets scattered by the gas or dust particles and gets re-emitted in different directions. So the spectral intensity is decreases with the height because the part of radiation is being absorbed and some of the radiation is getting scattered also. So this statement, that is the decreases the spectral intensity decreases in the upward direction, this statement is true. Now there is question 6. The atmospheric constituent responsible for upward infrared emission originating in the lower troposphere is carbon dioxide. Is it true or false? The atmospheric constituent which is responsible for the upward infrared radiation originating in the lower troposphere is carbon dioxide. Is it true or false? Question 6 is also true. The atmospheric constituent, carbon dioxide, is the main constituent which is responsible for the upward infrared emission originating from the lower troposphere. Question 5 and question 6 both are true. Now for the question 7. According to the Wind's law, if the temperature of the black body is tripled, what would happen to its peak wavelength, that is the lambda max? It will get halved, it will get doubled, it remains same, or it decreases. According to the Wind's law, what would happen if its black body temperature is tripled? What will happen for the lambda max when its black body temperature is tripled? It will get halved, it will get doubled, it remains same, it decreases. Of course, it will decrease as 3 times, because we know that the we know the Wind's law, which says the lambda t is equals to constant, and that constant value is often termed as the 3 into 10 to the power minus 3 in SI unit. So if the t is getting increased, then the lambda max would get decreased, and it will decrease by 3 times. Now for the question 8, calculate the total black body irradiance emitted by the Earth, assuming its surface temperature to be 255 Kelvin. You have to use here Stephen-Boltzmann constant, and this Stephen-Boltzmann constant has the value, has the unit, you can see, watt per meter square Kelvin to the power 4, watt per meter square Kelvin to the power 4. And so you do not need here for the calculating the any Earth's radius thing or any Earth sun distance. You can use the simple formula, flux is equals to sigma t to the power 4. So calculate the total black body irradiance emitted by Earth, assuming the surface temperature to be 255 Kelvin. Yes, the correct option is A, 239.7 watt per meter square. So this is the thing. So flux is equals to sigma t to the power 4. This is coming to 39.74 watt per meter square. And also there is question 9. In a one layer atmosphere model, the atmosphere radiates only downward. Is this statement is true or false? In a one layer atmospheric model, the atmosphere radiates only downward. This statement is true or false? Yes, This statement is false because we know the atmospheric models. Suppose this is a atmospheric model, what your atmosphere is the isothermal absorbing atmosphere. Now you know for the isothermal absorbing atmosphere there is the emission that happens both in the outward direction towards the space and also the downward direction towards the surface or ground. So this statement for this only radius downward, this statement is false. Now for the question 10, when a beam of radiation encounters an object like atmospheric gas or surface or anything, which of the following event can occur? That is transmission, reflection or scattering, absorption and the refraction. This is a multiple option correct question. You can see which of the when a beam of radiation encounters an object like the atmospheric gas or anything, which of the following events can occur? Transmission, reflection or scattering, absorption and the refraction. When beam of radiation encounters an object, all the following can occur. Transmission can occur, that is a part of its radiation can travel inside and then go outside. That we saw that this transmission coefficient is what amount of absorption, transmission absorption both occurs, and reflection or scattering and the refraction, both all this two can occur. That is, some amount of light is falling on the surface, it is reflected back, or some amount of light is falling in the surface and it is its path will be deviate from its actual path. So, yes. Yes, object means not a particle. Yes, they are the anything, any bar or slab, this kind of thing. Any bar or slab, there is also reflection or the refraction. These two events also happen. And this absorption, transmission, for accounting both, there is the optical depth of the medium or the optical depth of the slab. This alpha tau parameter comes. So for the question 10, all the 4 options will be correct. Question 11, a fraction of radiation absorbed by a gas is equal to the fraction of total backbody radiation emitted by the gas. This question is true or false? Also there is another question 12. You must you can mark to both the two and then we can discuss. The fraction of radiation absorbed by the gas is equal to fraction of total backbody radiation that is getting emitted by the same gas. This statement is true or false? And the next question 12 is, which atmospheric gas is primarily responsible for absorbing UV radiation in the wavelength range of 0.2 micrometer to 0.3 micrometer, breaking in the photodissociation reaction? That is water molecule or the water gas or the vapor, and the CO2 gas, ozone gas and the nitrous oxide gas. First is the question 11 and then question 12. Yes, question 11 is true. And question 12 is, which atmospheric gas absorbs UV? The UV that is within 0.2 micrometer to 300 micrometer, that is 200 nanometer to 300 nanometer range, and then gets photodissociated. That is, photodissociated UV photodissociation means the UV photodissociation of that gas means, of course, there will be O3 is the correct option. Yes. And now for the second question, the photodissociation of O3 gas produce oxygen and the oxygen atom. This process, this ultraviolet radiation band has a term, that is the Hartley-Huygens band, where ozone strongly absorbs UV light, and this photodissociation reaction is O3 plus H2 is equals to O2 plus oxygen, and this process is crucial for the harmful UVB or UVC radiation. And other gases such as the water vapor absorbs mainly in infrared. It is not a UV absorber, and carbon dioxide also absorbs infrared, but not in the range of H2O, or CO2 has no strong absorption signature in 200 nanometer to 300 nanometer band, and nitrous oxide has the absorption signature below the 200 nanometer band, and ozone is the main contributor for the absorption and 200 to 300 nanometer band. And also the first question, that is the question number 11, this statement is a direct consequences of the Kirchhoff's law, where emissivity is equals to absorptivity for a black body. So at the thermal equilibrium, the fraction of black body radiation emitted at the wavelength lambda and the fraction of incident radiation absorbed at that wavelength lambda, both are equal. So a gas that absorbs radiation emit the same amount of radiation at the same wavelength. So for the question 11 and question 12, question 11 option A correct, and question 12 option C correct. And question 13, if atmosphere absorbs 100% of thermal radiation, then the surface temperature would be Ts is equals to 2 to the power half into Te. That is emission temperature is equal, that is the surface temperature in terms of emission temperature formula is given by this. This question is correct or incorrect? This kind of questions are simply from the models which were discussed in the class. So the same isothermal absorbing atmosphere model is written here, where you have seen that there is an atmosphere, there is a surface, S0 by 4 1 minus alpha, that is the solar radiation that is coming in the system. Now the ground also emits sigma T to the power 4, and the atmosphere emits in the two-way direction, that is sigma Ta to the power 4 and in the space side, and sigma Ta to the power 4 in the lower ground side, and this is also absorbed by the ground. So we can write equation in the three regions. First region, which is in the space. So for the space region, also the sigma Ts to the power 4, this is going to this atmosphere, and F into sigma Ts to the power 4 portion is absorbing by this, and 1 minus F into sigma Ts to the power 4, that portion is being emitted from the atmosphere. So there are some equations you have to write in different regime. So for the first equation is S0 by 4 into 1 minus alpha is equals to sigma T to the power 4. T is the emission temperature of the earth or the system. And also for the space, you have to balance both incoming and the outgoing. So for the space, the incoming radiation was S0 by 4 1 minus alpha, and the outgoing factor is a factor of sigma Ta to the power 4, that is being emitted by the atmosphere, and also a factor 1 minus f into sigma Ts to the power 4, that is the what fraction of the ground's radiation could not be absorbed by the atmosphere. So this is for the space, and for the atmosphere layer, there is emitted part is 2 sigma Ta to the power 4, and the absorbed part is f into sigma Ts to the power 4. And for the ground, this is simply S0 by 4 1 minus alpha is equals to sigma Ta to the power Ts to the power 4. And also sigma by 4 1 minus alpha must be added with the sigma Ta to the power 4. So for this, from this 1, 2, 3, 4 equations, you will get the surface temperature of the earth as a earth or system as a function of the emission temperature, that is the 2 by 2 minus f to the power 1 by 4 or 0.25 factor. So here if you put f is equals to 1, then you will get 2 to the power 0.25 into Te. So for this question, Ts is equals to 2 to the power 1 by 4 into Te is true when the atmosphere absorbs the 100% of thermal radiation. Now comes the question 14. If the outgoing long wave radiation or OLR is 240 watt per meter square and our solar irradiance is 1360 watt per meter square, Earth's albedo assuming the energy balance is dash. Answer up to 3 decimal places. If outgoing long wave radiation is 240 watt per meter square and the solar constant is 1360 watt per meter square, find the Earth's albedo assuming the energy balance. The solar constant is S, that is equal to 1360 watt per meter square, and the incoming is equals to outgoing. Outgoing long wave radiation is given, and also incoming radiation can be written as the S0 by 4 into 1 minus alpha, where S0 is the solar constant, that is 1360 watt per meter square. So the equation that is equals to incoming is equals to outgoing, that can be written as the S0 by 4 into 1 minus alpha is equals to outgoing long wave radiation factor, that is 240 watt per meter square. Here the options are S is equals to 1360 by 4 1 minus alpha is equals to 240. So 1 minus alpha is coming about 0.7058 or 7.01 minus alpha factor is coming 0.706. Now alpha is equals to 1 minus answer, that is 0.294. Alpha is coming to be 0.294, that is reflectivity of Earth surface. So this equation we can check, Earth's albedo calculated given value from the question. So this is coming around 0.294. Alpha is Earth's albedo, and this can be written as the what amount of radiation is reflected back from the Earth, what amount of the solar radiation is emitting back from the to the space, and the equation here is used is by 4 into 1 minus alpha is equals to outgoing log of radiation. Now for the question 15, the lowest albedo is found over oceans in the subtropical regions due to low cloud cover and a dark ocean current. This statement is true or false? The lowest albedo is found over the oceans in subtropical regions due to the low cloud cover and the dark ocean currents, dark ocean surfaces. This is true or false? We will discuss question 15 and question 16 both at a time. And question 16 is, which of the following would happen if Earth has no atmosphere? That is, the emission temperature of Earth will be surface temperature of Earth. Emission temperature of Earth is greater than the surface temperature of Earth. Emission temperature of Earth is less than surface temperature of Earth. Surface temperature of Earth would be warmer. What would happen if Earth had no atmosphere? That is, emission T is equals to Ts, or Te will be greater than Ts, or T would be less than Ts, or the surface temperature of Earth would be warmer. Yeah, question 15, sorry. So this comes to description of question 13, and also this question 15 is true because the clear subtropical ocean region, that is dark water plus little cloud, produces lowest surface plus sky albedo on the Earth, and the lowest albedo region is found near the subtropic. And question 16, sorry, the emission temperature of the Earth would be equal to the surface temperature of the Earth if there was no atmosphere, because then the surface would be surface radiation would directly go to the space, and so the effective temperature equals to the surface temperature, and temperature would be about 255 Kelvin, colder than the current value, that is about 15 degrees Celsius, 15.2 degrees Celsius, Celsius, that is found in now. And also this thing can be just be checked from this equation, that is, if F is equals to 0, that is no fraction, there is no atmosphere suppose, so there will be no absorption, so you can put F is equals to 0 here, so 1 to the power 0.25, so Ts is equals to Te. So this thing directly comes if there is so this thing directly comes from this equation. And also you can check that if anyhow this atmosphere do not absorb very well, that for a system, suppose there is any arbitrary system, There is F is about 0.05 or 0.005, then you can say that the TS will move towards the TE. Now for the question 17, the Earth's surface is in radiative equilibrium. The incoming solar radiation incident upon the surface is 300 watt per meter square. The surface receives 150 watt per meter square downward long wave radiation from the atmosphere. The outgoing long wave radiation radiation emitted by the surface is observed to be 450 watt per meter square. Based on energy balance, what will be the value of the surface albedo? Suppose the system that is in radiative equilibrium. So the incoming solar radiation that is incident upon the surface is 300 watt per meter square. The surface also receives 150 watt per meter square of downward long wave radiation, that is from the atmosphere. The outgoing long wave radiation that is emitted by the surface is observed to be 450 watt per meter square. So what would be the surface's albedo? Sorry. We know the A fraction of the incoming solar radiation would be reflected back. If that fraction is alpha, that is alpha into 300 watt per meter square would be reflected back, and the 1 minus alpha into 300 watt per meter square, that would be incident on the surface. Also, then the received radiation on the surface would be 300 into 1 minus alpha plus the 150 watt per meter square that is coming downward from the atmosphere itself, and also the outgoing long wave radiation value is given, that is 450 watt per meter square. Based on this values, what will be the surface albedo? Yes, the surface albedo would be 0. So here the incoming short wave at the surface is 300 watt per meter square. Downward long wave is 150 watt per meter square, and outgoing long wave is 450 watt per meter square unit, of course. So for the surface, you can for the surface it is 1 minus alpha into 1 minus alpha into 300 watt per meter square plus the fraction which is coming from the atmosphere itself is equals to the outgoing thing. This corresponds to alpha is equals to 0. So all the radiation that is falling on the surface is being absorbed. There is no reflection in the system. Now the question 18. See this figure. Which season shows the warmer polar stratosphere in the winter hemisphere? So this question is a bit tricky and we could not and I could not give answer. You were telling right. So for this kind of question, first you have to find which is the winter hemisphere. So for the December, January, February, the winter hemisphere is the northern hemisphere, and in the northern hemisphere you have to find the temperature of the polar stratosphere. For the stratosphere temperature, we are considering about 25 kilometer above the surface, and about, suppose, at 80 degree north. At 80 degree north, at in the December, January, February, the temperature is around 210. And also for the June, July, August, this season, winter hemisphere is a southern region or the southern hemisphere. Now then the temperature at the 80 degrees south is about 190 Kelvin. So for this question 18, in the December, January, February, the northern hemisphere will be warmer. Question 18, option A is correct. Just by looking the contours and the height of the stratosphere and also the variation of the seasons. Question 18, option A is correct. Yes. Polar regions in summer have a positive net imbalance as they receive sunlight for 24 hours. This statement is true or false? Question 19. Yes, question 19 is true. This polar region have a positive net radiation imbalance due as they receive sunlight for the 24 hours in summer. And question 20 is, which of the following statements are true regarding the effective temperature of Earth that is described in your lectures? And this is the actual measured average surface temperature of Earth. It is calculated mathematically based on the balance between absorbed solar radiation and emitted infrared radiation, assuming Earth acts as a black body. Its value is approximately given as 255 Kelvin. It is higher than the actual surface temperature due to atmospheric reflection. Question 20. Of course, option B and option C are correct. This is not the average surface temperature of Earth because it is 255 Kelvin. That is less than, of course, less than 273 Kelvin. That is, it is in the minus domain. Earth's average surface temperature is not minus something. It is about 15 Kelvin. And it is higher than the actual surface temperature. This statement is also false. So question 20, option B and C are correct. Question 21 is another math question. Venus is at 1.08 into 10 to the power 6 kilometer for the sun. Its albedo is 0.75. Its effective temperature is how? You can give the formula here which you can use. So here you have to use the same formula, that is by 4 into 1 minus alpha is equals to sigma t e to the power 4. But the main thing is here S is not equals to for the Earth. Here S must be calculated from the S should be calculated from the Earth Venus distance. So for the S Venus is equals to ES dot, that is energy emitted per unit time from the Sun, by the 4 pi Earth square. R is the distance from Sun to Venus, and you can calculate the alpha value, the corresponding S and corresponding alpha value. We will update this answers in the drive. And question 22, I am skipping the question 21 now for the time. And question 22, let's go to question 22. That is, emissivity is a surface property that varies between 0 to 1, where emissivity is equals to 0 for a black body. This statement is true or false? Emissivity is a surface property that varies in between 0 and 1, where emissivity 0 is for a black body. We know the black body is a perfect emitter, and for the perfect emitter the emissivity is equals to 1, not 0. Emissivity 0 is for the absorber, the total absorber, the system which totally absorbs the radiation what is falling on it, and this statement is false. Now question 23, which of the following best describes the role of emissivity in the Stephen-Boltzmann law? It increases the solar radiation absorbed. It is always 0 for the real materials. It determines the efficiency of a surface in emitting radiation. It reduces the incoming solar radiation. So the emitted flux is of course always written as flux is equals to emissivity into sigma T to the power 4. This is the modified version of the Stephen-Boltzmann law if the EPSA has there is EPSA variation. So which of the following best describes the role of emissivity in Stephen-Boltzmann law? So flux from an emitted surface is written as sigma T to the power 4 into emissivity into area. It determines the efficiency of the surface in the emitting radiation. This thing, question 23, option C is of course correct, because emissivity 0 is no emission. There is nothing to with the solar radiation and the Stephen-Boltzmann law. 23 option C is correct. 22 option this statement is false. Now question 24, you can calculate this. Calculate the temperature in degrees Celsius for a object which has the radiant energy of 4.5927 into 10 to the power minus 5 kilowatt per centimeter square. Calculate the temperature for an object which has radiant energy of 4.5927 into 10 to the power minus 5 kilowatt per centimeter square. So now for this kind of question, you must have to convert this kilowatt per centimeter square unit to the SI unit, that is meter kilometer second MKS unit. And you can kilowatt, you can write 10 to the power 3 watt. And for the centimeter to meter conversion you have to do. So you know 1 centimeter is equals to 10 to the power minus 2 meter. So you must have to write 2 times 10 to the power minus 2. So if you just do the calculation, you will find that is coming around 299.95 Kelvin. This is 80 point. This is coming around 29 Kelvin. This is around 26.5 degrees Celsius. Question 24 is coming around 26.5 degrees Celsius. And question 25, in the one layer atmospheric model, the atmosphere radiates only outward direction to the space. This is false, of course. This is the same question. And question 26, if Earth's albedo increases, what happens to the mean emission temperature? You must know, you must memorize the formulas of the emission temperature as a function of the incoming solar irradiance. So as by 4 into 1 minus alpha is equals to sigma T to the power 4. So this equation, check this equation. So this question is from this equation, that is the S by 4 into 1 minus alpha is equals to sigma T to the power 4. If the alpha increases, then this factor will decrease, and this will decrease the emission temperature. So from this equation you can say that when alpha albedo increases, the S0 by 4 into 1 minus alpha, this factor decreases. So of course TE decreases. Question 26, question 26, option B correct. And here is a question 27. Which of the following statements are correct? Black body has emissivity 1. Sun is a black body approximately with temperature 6000 Kelvin. Greenhouse gas absorb long wave radiation and re-emit it, warming the lower atmosphere. The Stephen-Boltzmann law is sigma T to the power 4. And without an atmosphere, Earth's surface temperature would be higher than it's now. Which of the following options are correct? Also energy per unit area, energy emitted per unit time. Yes, only energy per unit time per unit area, that would be correct. Flux is equals to sigma T to the power 4, not energy. So only A and B, these two options are correct, and C and D are incorrect. Now for the question 28, the saturated adiabatic lapse rate is less than adiabatic lapse rate primarily because saturated air is denser than dry air. Condensation of water vapor releases latent heat into the air parcel. Dry air expands rapidly when it is rising, and saturated air contains less oxygen. Saturated air is denser than the dry air. Condensation of water vapor releases latent heat into the air parcel. Dry air expands more rapidly when rising. Saturated air contains less oxygen. You have seen the formula for the adiabatic TS and TD here in the first two questions, where you have seen that this adiabatic lapse rate and the TD, these are related by the latent heat a function of latent heat. So the question for this kind of question, condensation of water vapor releases latent heat into the air parcel, this thing is correct. So correct option would be B, because the dry air adiabatic lapse rate is found to be 9.8 Kelvin per kilometer, applies when rising air is unsaturated, that is no condensation is happening here. Cooling is done only by adiabatic expansion, and the saturated lapse rate is about 4 to 7 Kelvin per kilometer. And when a air parcel is saturated, water vapor condenses as the parcel rises and cools. This condensation releases latent heat, and the heat partially offsets the adiabatic cooling, so the parcel cools more slowly. And it is found that the TS and the TD are TS is always less than TD in the stable in stable or unstable any kind of condition. And also TS and TD relation is given to you in your lecture. Question 29. Dash is the temperature that a moist air parcel would have if all its moisture were condensed out under the adiabatic condition and was adiabatically compressed or expanded to the reference temperature P0. Here the definition of fourth temperature should be discussed once again. That is the virtual temperature, virtual temperature, equivalent potential temperature, and the polytropic potential temperature. Now the virtual temperature or the TV, this accounts effect of water vapor on air density. Moist air is less dense than the dry air at the same temperature and pressure. So the virtual temperature of dry air need to have the match the density of the moist air. The virtual temperature can be written as T into 1 plus 0.61 into Q, and this temperature T is the actual temperature of the air parcels. Q is the specific humidity, that is what is the amount of water vapor in kg unit in the per kg of moist air, and 0.61 is the coming from the ratio of the vapor gas constant and the dry air gas constant. And virtual temperature correction to the equation of state is written as this formula, and there is an equivalent temperature that is measured to be as the temperature a air parcel would have if it is brought adiabatically to P0 reference temperature, that is 1 bar temperature 1 bar pressure, and all the moisture were condensed out, releasing the latent heat. So the equivalent potential temperature formula is also given you can find that the equivalent potential temperature is equals to potential temperature into exponential LV/RS Cp in by T. LV/RS exponential LV/RS by Cp T, and also the potential temperature formula, you know, that is equals to temperature of the parcel into P0 by P to the power kappa. Kappa is the factor of R by Cp, that is the R is equals to RD, or the dry air's gas constant, and Cp value, you know, this is coming around 0.286, and the polytropic temperature, this is a generalization of the potential temperature for a process where pressure and the temperature follows the polytropic relation, that is Pv to the power gamma, or Pv to the power n is constant, and the polytropic temperature equation is written as this: P polytropic is equals to temperature into P0 by P, where P0 is 1 bar or 1000 hectopascal unit, and to the power factor is n minus 1 by n, and this for the dry adiabatic case, n is equals to gamma is equals to Cp by Cv. This reduces for the dry adiabatic case, theta polytropic is equals to theta potential, that is theta potential. Now here for this question, dash is the temperature that a moist air parcel would have if all its moisture were condensed out under adiabatic condition and was adiabatically compressed or expanded to the reference temperature P0. For all the moisture to be condensed out under adiabatic condition, there would be some emission of latent heat, of course. So the temperature would have some factor of latent heat, and from this perspective the equivalent potential temperature, this option is correct. So while this kind of question, if you cannot remember what are these temperatures, then you can just check the what is, if any hint was given in the question itself, that all its moisture were condensed out. So when the all heats of moisture will be condensed out, there will be release of some latent heat. So any temperature of the system would contain some factor of this latent heat kind of thing, because all the thing was condensed out in the adiabatic condition. So from that perspective you can mark this questions. Question 29, option B is correct. Question 30. A black body is a perfect absorber and emitter with emissivity 1. This question is true or false? Yes, black body is a perfect emitter and also perfect absorber. This question is true. Question 30, correct option is true. Question 31. An air parcel starts at a pressure of 950 hectopascal and has its temperature of 22 degrees Celsius, that is 22 plus 273, that is 295 Kelvin. It is lifted adiabatically. The environmental temperature is 700 hectopascal and it is measured to be at 273 Kelvin or 0 degrees Celsius. You have given the value of R by Cp, that is 0.286, and the reference pressure, the 1 bar or 1000 hectopascal. Now calculate the potential temperature of the air parcel in, of course, Kelvin unit. You know the equation of the potential temperature, that is potential temperature is equals to temperature of air parcel into P0 by P, where P0 is 1000 hectopascal and the P is 950 hectopascal. and there is a to the power factor of R by Cp, that is given here already, 0.286. And this equation of the potential temperature has no dependence on the environmental temperature of system or environmental pressure of system. Sorry if any by any mistake maybe I have some in some place I can call it the P. P is the pressure, of course. The potential temperature is a function of pressure and temperature both, but not any dependence on environmental temperature or pressure. Just the temperature and the pressure of the air parcel have the significance. So for question 31, so question 31 is coming around 305 Kelvin. So here option A is correct. At multiple of 50 or 100 the options are given. So if you do not find the correct answer or the correct decimal place, you can mark the nearest integer or nearest multiple, 1000 multiple or 50 multiple in which order the options has been given in the question. So question 31 option A is correct. Question 32, the plane of circle of illumination of Earth is aligned with the Earth's axis. This statement is true or false? The plane of circle of illumination of Earth is aligned to Earth axis. This statement is true or false? Yes, this question is false because the definition of circle of illumination is given as the boundary between the day side and the night side. So its plane is always perpendicular to the incoming solar rays or the solar radiation. So it does not align to the Earth's axis, or the axis. Earth's axis means the axis along which the Earth is rotating. Earth axis is tilted at 2 to 3.5 degree to the plane of its orbit. The orbit of illumination is generally not aligned with the axis except on the equinoxes, when the circle of illumination passes through both the poles. So question 32 is false and 31 was 300 Kelvin, this option A. Now question 34 and question 33 and the 34. 33 is, what is the amount of energy in petawatt that is emitted by a planet having the temperature 30 degrees Celsius? The emissivity is 0.4 and the diameter of the planet is 12800 kilometer, and sigma values are given. So here you can see that is the dP is given, and so Rp you can calculate. Here the amount of radiation energy in watt unit, that will be 4 pi into Rp square into sigma T planet to the power 4 into epsilon P, that is given as 0.4. So Rp is equals to 0. 0.64 into 10 to the power 4 kilometer. So 4 pi into 0.64 into 10 to the power. Tp is 303 to the power 4. That's a P is 0.4. And you have to convert this all this in the petawatt. Sorry. So this is coming. Yes, this is coming approximately 100 petawatts. Okay, yes. And question 34 is the amount of energy that is received in the unit of time on the unit area perpendicular to the sun's direction at the mean distance of earth from the earth from sun is called solar radiation, solar constant, solar intensity of solar radiation, and the air mass. The amount of energy received per unit time on a unit perpendicular to the sun direction on a unit area that is perpendicular to the sun's direction at the mean intensity of mean distance of earth from the sun is called the I guess this is solar constant. I have to confirm this once again. Currently I cannot do. The amount of radiation energy is a solar constant or intensity of solar radiation. Maybe it is solar intensity of solar. Yes, question 34, intensity of solar radiation. It is, of course, you are correct. And question 35, on a equinox, approximately how many hours of daylight does the location on equator receives? On the equinox, approximately how many hours of daylight does the location of equator receives? Yes, the approximately 12 hours of daylight the equator receives. And also in the June solstice, the approximately how many hours of daylight does the location at the 70° northern latitude experience? This is at the 24 hours daylight because this is called the midnight sun. This will be this 60° north will be within the Arctic Circle. So here there will be 24 hours. And question 37, on an equinox, all locations of earth receive approximately 12 hours of daylight. This statement is true or false? Of course, this statement is false. Only the equator receives on the equinoxes. Only the equator, that is 0° region, 0 degree latitude will receive 12 hours of daylight. Question 37 option is false. Question 38, 39 and 40. You have to solve the 3 questions at a time and then I will discuss. So the adiabatic lapse rate of moist air is greater than adiabatic lapse rate of dry air, lesser than adiabatic lapse rate of dry air, equals to adiabatic lapse rate of dry air, depends on the latitude of the location. Question 38. You know that the adiabatic lapse rate of moist air, that is of the saturated air, that the tau is less than tau t always. So the option B is correct. And question 39. A location has environmental lapse rate of 7 km per second. 7 Kelvin per kilometer. Sorry for the mistake. The moist adiabatic lapse rate is 6 Kelvin per kilometer. The atmosphere is conditionally stable, unconditionally unstable, conditionally stable, none of the above. Yes, if this is MCQ, then which option will be correct? Suppose this is given as MCQ, then this is unconditionally stable. Option A is correct. And question 40. What are the possible consequences of increase in atmospheric water vapor content? Water vapor acts as a heat trapping greenhouse gas similar to carbon dioxide. Increased water vapor enhances cloud formation, which can influence Earth's radiation balance. It leads to negative feedback that cools the atmosphere's surface, Earth's surface. Water vapor precipitates in the positive feedback loop that amplifies global warming. Yes, for this question only C is wrong. The negative feedback, only the aerosols in the atmosphere can cause the negative feedback. All the other constituents such as carbon dioxide and gas, they are responsible for the positive feedback. And this water vapor acts as a heat trapping greenhouse gas. This statement is correct. Increased water vapor, of course, enhances clouds formation. So Earth's radiation balance will be affected because the clouds are the main factor for the Earth's albedo. That is what amount of incident solar radiation is going outward in the space. And the next question statement, that is the water vapor precipitates in the positive participates in the positive feedback loop that amplifies global warming. Of course, water vapor absorbs in the outgoing lava radiation from the Earth's surface, so they act as a heat trapping agent in the atmosphere. Now for the question 41 and 42, consider the following statements. Longitudes are the angular distance of the distance of a plane from the equator, and the latitudes are the angular distance of a place from the prime meridian. Which of the statements are true or false? Yes, both these questions or both this statement in the questions are true. Longitudes are determined to be a angular distance from a for a place from the equator itself, and the latitudes are the angular distance from a place from the prime meridian of Earth. So option C is correct. And also, what is the sun's declination angle during summer and the winter solstice? That is 23.5 degree, minus 23.5 degree, and this 0.53 degree and 53 degree, and 53 degree, 32 minutes and 74 minutes, and also minus 23.5 degree and 66.5 minutes. Yes, question 41 is E, correct. Sun's declination angle varies from plus 23.5 degree to minus 23.5 degree during from the summer solstice to winter solstice. And here is the question 43. The average solar irradiance that is received by the Earth, the average solar irradiance received by Earth on the top of atmosphere per unit surface area is dash watt per meter square. Yes, that is 1360 watt per meter square. And of course that is coming from the formula, that is energy emitted per unit time from the sun by 4 pi distance, 4 pi r square. R is the earth sun distance. In earth sun distance, if you consider all the thing in the SI unit, you can find this 1360 watt per meter square. So what effect would be absent in the planet without atmosphere? Attenuation, beam spreading, both of them should be absent, and neither of them should be absent. What effect would be present in a planet without an atmosphere? Attenuation, beam spreading, both of them will be absent, and neither of them would be absent. Yes, both of them will be absent, attenuation and beam spreading. Now question 45. Dash is the imaginary plane that bisects question 45. Dash is an imaginary plane that bisects both Earth and Sun. Equatorial plane, meridional plane, plane of ecliptic, and plane of illumination. Which one is correct? This is plane of the imaginary plane which bisects both Earth and Sun is known as the plane of ecliptic. And also the question 46. The axis of Earth always remains parallel to itself in all its position along the Earth's orbit around the Sun. That is called, this axis is called the axis of Earth always remains parallel to itself in all its position along the Earth's orbit around the Sun. This thing is called parallelism, Earth's tilt, axial tilt, obliquity, and ellipse. This thing is called the parallelism. Option A is correct. Now the question 47. What is the mean temperature of Earth's surface today due to global warming? 15.2 degrees Celsius, 16.4 degrees Celsius, 18.4 degrees Celsius, 14.8 degrees Celsius, and 12.5 degrees Celsius. Yes, 15.2 degrees Celsius, and before industrialization this temperature was 14 degrees Celsius. And the next question, we would not calculate it today. You can find this from your lectures. What is the value of the solar irradiance of Venus? So the solar irradiance of Venus is calculated to be the amount of energy emitted by the sun per unit time by the distance from sun to Venus. So this calculation is given in your lecture and I will not consider this today. And the next question is, what does the term planetary albedo represents in the context of Earth's energy balance? The fraction of solar radiation that is getting absorbed by the atmosphere, the fraction of solar radiation that is reflected by the Earth's surface and atmosphere, the total solar radiation that is received at the top of atmosphere, the net absorbed radiation by the Earth's surface, the percentage of solar radiation that is converted into thermal energy. What does the term planetary albedo refers in the context of Earth's energy balance? Huh? Yes? Okay. Okay. Is it visible now? Okay. What does the planetary albedo represents in the context of Earth's energy balance? The fraction of solar radiation absorbed by the atmosphere, the fraction of solar radiation that is reflected by the Earth's surface and atmosphere, the total solar radiation that is received at the top of atmosphere, the net absorbed radiation by Earth's surface, the percentage of solar radiation that gets converted to the thermal energy. Yes, for the planetary albedo, the reflection part is referred as referred. So question 50, the last question for today. Which of the following factors contribute to the mean blackbody emission temperature of Earth? Earth's albedo, atmospheric absorption, surface emissivity, and Earth's radius. Which of the following factors contribute to the mean blackbody emission temperature of the Earth? Mean blackbody temperature or the mean emission temperature T, that is related to is 0 by 4 into 1 minus alpha. So only the alpha factor and the energy which is received at the top of atmosphere, this two factor has only relation with the blackbody emission T. So for this question 50, option A is correct. Now these two questions we can just discuss. As the Earth's mean blackbody emission temperature or the Earth's emission temperature is lower than surface temperature. You have seen that the Earth's blackbody emission temperature is 255 Kelvin, that is around 255 Kelvin, that is around 273 minus 255, that is around minus 18 degrees Celsius. But for the mean surface temperature, of course this surface temperature has time variation, but the surface temperature you can take this is mean surface temperature is about 273 plus 15 about 288 Kelvin or 15 degrees Celsius. So blackbody temperature is lower than the surface temperature. This statement is true. And the next question is, the mean albedo of Earth remains constant throughout the year. This statement is true or false? Yes, the mean albedo from the Earth remains constant throughout the year. This statement is false. Generally, Earth's mean planetary albedo, that is found to be the value of 0.3, and it do so the measurable variation from the seasonal variation and also the year to year variation. Though there is relatively small within the 0.01 to plus minus 0.02 that is observed over recent decades, and for this kind of albedo observation, Earth's albedo measurement, there are different satellite data. Some are the Ceres satellite data, and which has seen that the annual mean global albedo fluctuate from the 0.298 to 0.310. So you can see the fluctuation of the albedo is coming to the second decimal or third decimal place. From the other earth sign or other groundsmith methods, it has also detected the fluctuation is in the third order decimal place per year. So in the practice, Earth's yearly mean albedo varies less than 1 to 2% of its value, but these smaller shift can still matter to the climate energy distribution and the climate energy balance. So there is Earth albedo has different kind of variation, and this variation can cause for different typical activities such as the seasonal snow and the ice cover as the changes. It alters the surface reflectivity. Higher northern hemisphere has the higher albedo in the winter and the lower albedo in summer because of the because of the ice covered in the land, and cloud coverage changes due to different ocean currents, event, monsoon, etc. show the strong fluctuation of the Earth's albedo. Also, it has been seen that the inject of aerosol or the dust particle through some volcanic events can induce the fluctuation in the albedo value in the Earth. Also, anthropogenic aerosol must have the surface vegetation change. Those factors also influence the variation of Earth's albedo. So now question 52. 52 is our last question. We will discuss more questions tomorrow in the next class. I am stopping the presentation. Yes, thank you. Anyone have any question? Okay, thank you for joining. Yes. Anyone have any question or any remarks regarding the class? If nothing, then I am stopping the today's class, and also we will meet in the next class that will be on the next Sunday. Thank you for joining. Thank you. Yes, thank you.